stretching and shrinking. Vertical stretching away. Stretching the graph of f of x vertically away from the x-axis is given by some constant k times f of x provided that k is greater than 1. F of x stretches away from the x-axis by a factor of k. Consider f of x is equal to x squared, and one of its transformations is given by g of x equal to 2 times f of x. The graph of g of x is the result when f of x stretches away from the x-axis by a factor of 2. When we consider the graph of f, given by this reddish parabola here, its transformation, 2 times f of x, also called g, stretches away from the x-axis. So from the perspective of the x-axis, g is further away than f. So we say this is stretching away from the x-axis by a factor of 2. Vertical shrinking towards. Shrinking the graph of f of x vertically towards the x-axis is given by k times f of x, provided that k is between 0 and 1. F of x shrinks towards the x-axis by a factor of k. Consider f of x is equal to x squared. One of its transformations, which we're going to call h of x, is equal to 0.5 times f of x. The graph h of x is the result when f of x shrinks towards the x-axis by a factor of 0.5. If we consider the meaning of the word shrink, it means something is getting smaller, it's going down. What vertically means it's up or down, so vertical shrinking means something is going down, getting closer to the ground. In our representation, let's consider the x-axis, the ground. The graph of the original function f is being pulled down towards the ground, the x-axis. Or in respect to the x-axis, if we're moving up, h of x is closer than f of x. When we consider the vertical shrinking or stretching of a parabola, we want to note that stretching the graph of a parabola vertically away from the x-axis and shrinking the graph vertically towards the x-axis does not change the vertex of the parabola if the vertex is on the x-axis. When we look at both cases, the vertex is still located at the origin, whether the graph is being stretched or if the graph is being shrunk. As we continue our discussion on vertical stretch and shrink, we're now going to focus on the value of k and the algebraic representation, how it affects the graph. So let's use the function f of x is equal to x squared minus 1 for each problem below. What is the transformation that occurred on f of x? And we have 3 cases we're considering. 3 times f of x, 5 times f of x, and 1/2 times f of x. In case A, f of x stretches away from the x-axis by a factor of 3. In case B, f of x stretches away from the x-axis by a factor of 5. And in case C, f of x shrinks towards the x-axis by a factor of 1/2. When we consider vertical stretching and shrinking, we say that in general it's going to be the factor k times the function f of x. If k is greater than 1, which we have in cases A and B, then the f of x, the function, will stretch away from the x-axis. But if k is between 0 and 1, then we say f of x shrinks towards the x-axis. So once again, the factor k multiplied by the function, it indicates there's a vertical stretch and shrink. If k is greater than 1, the function will stretch away from the x-axis. If k is between 0 and 1, the function will shrink towards the x-axis. Let f of x equal 4x minus x squared. Its graph is displayed to the right along with its transformation. G of x is equal to k times f of x. Using the graph and the information we get from this graph, find k. The answer is the vertex of f is at 2, 4, and the vertex of g is at 2, 8, which indicates that f of x value doubles, so k is equal to 2. It's not clearly stated, but by indirectly we see that the vertex is at 2, 4 right here, which means that f of 2 is equal to 4. And g of 2 is equal to 8. Since the value doubled, we know that g of x is equal to some number times f of x, so g of x must equal 2 times f of x, since the value of f of x doubled going from here to here. Now, one other note. I did use the vertex because that's an easy point to locate. However, we're not limited to using the vertex. We can use any point on the graph. For example, if I used 1, 3, I can see that 1, 6 is also on the graph. That y value also doubles. And now we're going to turn our attention to horizontal stretching and shrinking. Stretching the graph of f of x horizontally away from the y-axis is given by f of kx, provided that k is between 1 and 0. Let's pause here for a minute. Before we were talking about vertical stretching and shrinking, and that was from the perspective of the x-axis. But now that we're talking about stretching and shrinking a graph horizontally, this is going to be from the perspective of the y-axis. Note the change in the notation. When we were talking about vertical stretching and shrinking, the constant k was multiplying f. Now the constant k is multiplying x. So away, we're going to horizontally stretch away from the y-axis if the constant k multiplying x is between 0 and 1. Continuing on with this discussion, f of x stretches away from the y-axis by a scalar of 1 over k. Let's consider f of x is equal to the square root of x and its transformation, h of x is equal to f of 0.5x. So this red graph here is the original function of f, the graph of the square root function. And when we multiply x by 0.5, notice that it's stretching horizontally away from the y-axis. So in perspective of the y-axis, the graph of f is closer to the y-axis, the graph of h is further away. Finally, the graph of h of x is the result when f of x stretches away from the y-axis. Shrinking the graph of f of x horizontally towards the y-axis is f of kx, provided that k is greater than 1. Notice that f of x shrinks towards the y-axis by a scalar of 1 over k, where k, the scale factor, is the inverse of this coefficient here. Let's consider f of x is equal to the square root of x, and its transformation, g of x, is equal to f of 2x. The graph of g of x is the result when f of x shrinks towards the y-axis. So here we have our original graph, the square root of x, f, and when we perform the transformation, f of 2x, notice that the graph shrinks towards the y-axis. Also notice that the x values get cut in half. Here the x value is 4, half of that is 2. That's the corresponding x value on the transformed graph. Now we're going to focus our value on the algebraic representation, specifically looking at the value of k and its effect on the graph. So let's let f of x is equal to 5 plus the absolute value of x. Write the transformation that occurs on f of x in these three cases: a, f of 2x, b, f of 6x, and c, f of 1/3 x. And here are the answers. F of x shrinks towards the y-axis by a scale factor of 1/2. Why is the scale factor 1/2? Remember that the scale factor is 1 over k. So whatever is the coefficient of x, we determine the scale factor by taking its inverse. In this case, the coefficient is 2, so the scale factor is 1 over 2, 1/2. The same is also true for letter b. F of x shrinks towards the y-axis by a factor of 1 over 6. However, in c, the coefficient is 1/3. So f of x stretches away from the y-axis by a factor of 3. 1 over 1/3 is equal to 3. Also take note that when k is greater than 1, as we have here, the coefficient of x is greater than 1, f of x will shrink towards the y-axis. When f of x is when k is between 0 and 1, as we have here, then f of x will stretch away from the y-axis. Let's look at a specific case of stretching away and how to determine the value of k. Let f of x equal 8x minus 2x squared. Its graph is displayed to the right along with its transformation g of x is equal to f of kx. We want to find k. So there's information on this graph that's going to help us determine the value of k. The answer is that the vertex of f is at 2, 8, and the vertex of g is at 4, 8, which indicates that the x value doubles. But remember, k will be the inverse of that. So k is equal to 1/2. Looking at the graph, I am going to write in the vertex of f, which is at 2, 8. Now notice the y values are the same, but the x values double, goes from 2 to 4. So if I had 2 times some number is equal to 4, obviously that number is equal to 2. But k is equal to the inverse of 2, the number I multiplied by. And the inverse of 2 is 1/2, and that's how we get k is equal to 1/2. Let f of x equal 0.5 times the quantity x plus 4 times the quantity x minus 2. Its graph is displayed to the right along with its transformation. G of x is equal to f of kx. We want to find k. The answer is that the vertex of f is located at -1, -4.5. And the vertex of g is located at -0.5, -4.5, which indicates the x value cuts in half. But remember, k will be the inverse of that, so k is equal to 2. I'm going to just indicate right here, this is the vertex of f. It's at when x is equal to -1. The vertex of g is when x is equal to -0.5. So -1 times something gave us -0.5. And that something is 1/2. But k is equal to the inverse of 1/2. And what's the inverse of 1/2? Is 2. In other words, if I solve for k, I would get 2.